Hello students, today we are doing 6.3, which is in general, we're doing Taylor and McLaurin series. I'm going to do it in two parts, so because this is a long section. So let's start with Taylor series. We said in the previous section that functions, if they are differentiable, then they can be presented as a linear function, as another function, right? So we can present a function as a series or as a polynomial. But not all functions were doable. Remember, we were restricted to some kind of functions only. So today we're going to show that probably every function, as long as it is differentiable, it can be presented as what? As a polynomial of degree infinity. I can change it from being a function that is complicated, like sine x, cosine x, to what? To a polynomial. And today we're going to do this one using Taylor series and McLaurin series. So let's suppose that f is any function, okay, that is differentiable at certain point A, at any point A. Then can we present a function, this function, as a infinite polynomial or polynomial of degree infinity or n? Yes, we can do that. And this is done by using Taylor series. So if f of x is a function, how do you present it as a Taylor series? It's the sum of n equals 0 to infinity of fna over n factorial times x minus a to the power n. This is called a Taylor series presentation of the function f of x centered at x equal to a. So this is a presentation of the function around some point a. Second thing, what is this notation here? This is the first time we see fn. Fn here, the function f to the power n, represents the function at a, represents the derivative of the function. So this is the nth derivative of f. For example, let's start with n equal to 0. So let's start with n equal to 0. What do we get in this polynomial when I put n equal to 0? We get n f 0 at a times x minus a to the power 0 over 0 factorial. So look at this series. It's a sum from n equals 0 to infinity. What if we started from 0, guys, when n is equal to 0? F0 means what? Do not differentiate the function. So I need the 0 derivative, means keep the function as is. So this is, we'll keep it as f of a. Okay, guys, be careful about the word. This is not a power. This is the derivative. The 0 derivative of the function means do not differentiate the function. So it remains, so it stays fa. Now, x minus a to the power 0, we know anything to the power 0 is 1. And this is 0 factorial is 1. So what are we left with? Just f of a. This is why the first term is f of a in Taylor. After 0, guys, we're going to go to n equal to 1. What happens when n is equal to 1? So what do we have in the second term? So we have f1 of a times, here we're going to replace n with 1. So x minus a to the power 1 over 1 factorial. And this is equal to, f1 means what now, guys? We're talking about the first derivative. So how do we write it? We write it as f prime at a times x minus a to the power 1 is x minus a over 1 factorial. Here it is, 1 factorial, you know, it's in only 1. So over 1 factorial, which is actually 1. And this is the term, guys, when n is equal to 1. What happens when n is equal to 2? Simply, I'm going to just do n equal to 2. The next term, we got f2 at a times x minus a square, right? Now we're going to replace n with a square over 2 factorial. What do we mean by f2 here? This power means what? The second derivative at a times x minus a square over 2 factorial. And this is actually the third term. So what do we have, guys? This is when n equals 0. This is when n equal to 1. And this is when n equal to 2. And this is when n equal to 3, this part. And goes on, right? It goes to infinity, n goes to infinity. Why do we have plus in between? Because of that sigma thing. This means what? The sum of the function. So the summation here, so we're adding from n equals 0, then plus n equal to 1, and goes on. So this is the expansion of Taylor series, guys. And what do you notice here? This is a number. This part is a number. This one also is a constant. This is also a constant. Those are numbers. This is also a constant. So look at this. The first thing, there's a constant, then a constant times a polynomial of degree 1, polynomial of degree 2, polynomial of degree 3, right? X minus a cube, and goes on all the way to infinity. So I'm changing my function from being, for example, logarithmic function, a sine function, cosine function, whatever function it is, I am changing it to a polynomial by using what's called Taylor series. Second part is the McLaurin now. We're going to go to the McLaurin series. What's the difference between Taylor and McLaurin? It's the same thing, guys. The only difference is that A here is always 0. And that was a very special case in Taylor. So McLaurin is a special case in Taylor series. So whenever A is equal to 0, it was discovered by McLaurin that this kind of series has a unique features. We're going to talk about it in a minute, guys. Okay, so look at the expansion. When n is equal to 0, you get f0 of 0 over n factorial. And you know 0 factorial is 1, and x to the 0 is 1. So this is what you get for the first term, is f0, right? So let's take n equal to 0. What do we get in this case? We're going to start with n equals 0. So this is f0 at 0 times x to the 0 over 0 factorial. And 0 factorial is 1, and x to the 0 is 1. So we are left with what? F at 0. Why f of 0? Because what does that mean? It means the 0 derivatives, means do not differentiate. And this is the first term in McLaurin series. Notice, remember, in Taylor series, if you go back, it says x minus a, isn't it? It says x, but a here is 0, so there is no a anymore. See? So it's only x to the n. This is why you see only x to the n, right? So this is a special case of Taylor series. And this series is called the McLaurin series. So McLaurin series, all you have to do is to replace a equals 0 in the Taylor series, and you will get McLaurin series. Let's look at this examples now. Find the Taylor series of f of x equal e to the x at a equal to 2. You know, e to the x is another kind of function. It's not a polynomial. So can we present it as a polynomial? Yes, we can. So what do we start with, guys? The first thing we start with is that we have to write the Taylor series. F of x, the expansion of Taylor series, is what's the first thing? F of a. Now here, look, a is 2. So this is f of 2. And you can see this is Taylor series. I actually copied it here, f of 2. Plus what? The next one is f prime at 2 times x minus a over 1 factorial plus f double prime at a times x minus a square over 2 factorial. I'm forgetting actually the a is 2, so I better fix it before we go further. So this a is 2, and this a is 2. X minus 2, and this is x minus 2 square, plus f triple prime of 2, and this is also 2, by the way. We have to change that one to 2. Then x minus 2 cube over 3 factorial plus f4, the fourth derivative, at 2 times x minus 2 to the power 4 over 4 factorial plus that. I always like to expand my function up to what? Up to the fourth derivative, so I can see what is the trend here. Okay, if you stop at the second derivative, you see, because at the end you have to represent the function as a series. So this all of expansion, this is the expansion of the series. So I have to go back and present it as what? As a series, you see? So this is the target. How do I do that? In order to do that, I prefer to go to the fourth derivative to see what's going on. Okay, And what's f of x here? It's our function, which is e to the x. So e to the x, which is f of x, is equal to all of this. So what are the things we have to find, guys, now? The things that we have to find are the following, the constants. So I need to know what's f of 2. And we have to find f prime of 2 over 1 factorial, etc. So we have to find those numbers. So all you have to do now is to focus at those values. So let's start with f of 2. Now, f of x in the question is e to the x. So this implies that f of 2 is what? E to the 2. So now we got the first one. Now let's go to the second one, which is f prime at 2. Now, f prime of x, if I differentiate e to the x, what do we get? Again, e to the x. So f prime at 2 is again e squared. And f double prime at x is again e to the x. So this implies f double prime at 2 is again e squared. And by the way, if you continue here, even if you continue up to the nth derivative of x, stays e to the x. So this function remains as is. So the nth derivative at 2 is nothing but e squared. So no matter how many times you differentiate it, it stays e to the x. So the derivative of the function at nth time, the nth derivative function at 2 remains e squared. So what do we do now? We go back to our function f of x. So therefore, now we can say, just 1 second. Okay, therefore, e to the x equal to f of 2 here is e squared, so it's e squared, then plus f prime at 2 is again e squared times x minus 2 over 2 factorial, right, over, this is, sorry, 1 factorial, plus f double prime again e squared, x minus a, x minus 2 square over 2 factorial, and goes on. Now let's present this one as a series, guys. As you see, there is always plus, there is always plus, so we're gonna present it as a plus. What do we have common here? You notice that e square is always there. So e square is in every term. Then what do we have, guys, here? We have x minus 2 to the power 1, x minus 2 square, and okay, when this is 1, there is 1 factorial, 2 factorial, so the next one is 3 factorial. So I can write this one as x minus 2 to the power n over n factorial. Of course, now n starts from where? N starts from 0 all the way what? To infinity. Why 0? Because the first term is, if you noticed, you have only x e squared. How can I write e squared? Isn't e squared equal to e squared times x minus 2 to the power 0 over 0 factorial? You know, because x, anything to the power of 0 is 0, is 1. So this is 1 and this is 1. So this can be written as that. So the first term here, if I put 0, I will get e squared, which is the first term. So this is, guys, the Taylor series presentation of e to the x at x, or at x equal to, or at a equal to 2, which means this is the Taylor series presentation of e to the x centered at x equal to 2. Let's look at sine x. I need to find the Taylor series presentation of sine x at a equal pi over 3. Same thing as I said before. We say that f of x, which is here sine x, is equal to what? It's equal to f, the first one, at pi over 3, right? That's the first thing, f of a, plus f prime at pi over 3, then times x minus a. Of course, a here, again, I always keep on writing this one as an a, where it should be replaced with pi over 3 here. So this one is pi over 3. And this is to the power 1 over 1 factorial, right? So this is to the power 1 over 1 factorial. Plus, the next term is f double prime at pi over 3 times x minus pi over 3 square over 2 factorial plus f triple prime at pi over 3 times x minus pi over 3 to the power 3 over 3 factorial plus f fourth prime at pi over 3 times x minus pi over 3 to the power 4 over 4 factorial, and it goes on. The polynomial continues. All right, so what's our target now, guys? As we said before, the only thing we need to look for is what are those functions? What are those values? Those are constants. Those are all constants. So we have f of x in the question is sine x. This implies that sine pi over 3 is equal to sine pi over 3 is a square root of 3 over 2, because pi over 3 is 60. Pi over 3 is 60. Pi is 180 divided by 3 is 60, and sine 60 is a square root of 3 over 2. Now we go to f prime at x. The derivative of this is cosine x. Now what do? We find cosine pi over 3. What's cosine of pi over 3? It's equal to half. Now let's go to the second derivative of x. The derivative of sine is negative sine x, and the second derivative at pi over 3 would be minus sine pi over 3, and this is negative root 3 over 2. So let's go now to the third derivative of x. The derivative of sine is cosine, and there's a minus, so this is minus cosine x, which means that the third derivative at pi over 3 is equal to minus cos pi over 3, which is negative half. Let's go to the last derivative, f fourth of x, guys. The derivative of cosine is minus sine, and there is a minus, so it becomes sine x. So you see the loop is closed now. We started with sine, we ended up with sine. So this implies that the fourth derivative at pi over 3 is nothing but sine pi over 3, which again takes me to square root of 3 over 2. Alrighty, now let's go back to our function. Therefore, now we go back to our original function. Sine x is equal to f of pi over 3, guys. The first one is f of pi over 3. F of pi over 3 is nothing but sine pi over 3. So this is, by the way, f of pi over 3, which is square root of 3 over 2. Plus, this one is f prime at pi over 3. So f prime, the second term here, would be half. Okay, so times half. Times what now? X minus pi over 3 to the power 1 over what? Over 1 factorial. Plus, the next one is f double prime. As you know, this is f double prime at pi over 3, which is going to be minus. So we replace this one with a minus. Let's see what happens. Minus square root of 3 over 2 times x minus pi over 3 square over 2 factorial. Now, the next one is also minus. So what do we say? Minus now. Half, because this one is what? F triple prime at pi over 3. So this is the third one, F double prime, triple prime. Then x minus pi over 3 to the power 3 over 3 factorial. The last one is this one, as you see, the fourth derivative. So this is the fourth derivative at pi over 3. So, and it's positive, so it's plus square root of 3 over 2 times x minus pi over 3 to the power 4 over 4 factorial, and we proceed. Goes continues to infinity. All right, now, so what I'm going to do now is I will split this into two parts, guys. Okay, so we will split it into two parts. I will take here, this is equal to the part that contains square root of 3 over 2. Here is a square root of 3 over 2, and here is a square root of 3 over 2, and here is a square root of 3 over 2. So I'm going to write this by itself. So this is a square root of 3 over 2. Then who's next? Minus square root of 3 over 2 times x minus pi over 3 square over 2 factorial. Then plus square root of 3 over 2 times x minus pi over 3 to the power 4 over 4 factorial. And of course, these continue to infinity. Then plus, now I'm going to go to the other part, change the color, and take another thing here. So let's use, for example, the black. Now let's focus at the half, guys. Half, here is half, and there's another half. So what do we have? So I'm going to write half plus half x minus pi over 3 to the power 1 over 1 factorial, right? Then we're going to come to this half, which is minus half x minus pi over 3 to the power 3 over 3 factorial. Now look at this one. This is positive, negative. Then the next one, I'm pretty sure is going to be positive. It alternates. That was 1, becomes a 3. So what do we say? Half x minus pi over 3 to the power 5 over what? 5 factorial, and plus dot, dot, dot. So now I have two series. I split it into two pieces. Now let's go to the green one. How can I present this as a series? I'm going to say this is the sum. Look at the power, guys. It's 2, 4. Who's that? So what should be here? What do you have here, guys? So we have here in the first term, there is nothing, but it's 2, 4. So since the power in this is even, so what do we say? It's always a square root of 3 over 2 times x minus pi over 3 to the power what? 2n over, you see, when this is 2, this is 2 factorial. When this is 4, this is 4 factorial. So again, 2n all factorial. This is how you present it. Of course, n starts from 0 to infinity for that part. It continues. See, there are dots here. Now, the question is, this series alternates. The first term is positive. The second one is negative. Then it's positive. So what should I say here? I should at the beginning put minus 1 to what power? Let's start with power n, guys. If I start with n equal to 0 and put minus 1 to the 0, anything to the power of 0 is 1, which is positive. So this will make the first term positive. So this is perfect and this works. So the green is done. Now let's go to the black one. Now plus the sum as, okay, let's look at the sum. You have half. In every time you have time, half, here's half. Now, The power here is 1, 3, 5. The power is odd. What's the best presentation for the odd arithmetic series? It's 2n plus 1, isn't it? So you have 2n plus 1. That's a good presentation of the odd powers or odd numbers. You see, when this is 1 factorial, 3 factorial. So it's going to be also 2n plus 1 factorial. And as usual, n starts from 0 to infinity. Now, let's look at the terms. The first one is positive. So I'm going to start with mine. I'm going to put minus 1 to the power n. Will the n work if I started with this? Yeah. And when I put n equals 0, what's the first term? It's going to be 0, which is positive, and this is good because the first term is positive. Put 1 will be negative, and this will make it, work for the presentation. And if, by the way, if you take n equals 0, this is going to go, and you still remain with 1, and this is the first term, which is to the power 1. So this is the power series presentation of the function sine x around pi over 3. It has 2 power series. I can split that. So this is one of the unique things about the Taylor series. Can be presented and as a sum of 2 series. All right, let's look at cosine around pi over 2, guys. Okay, so we're going to present cosine around pi over 2. To do that, we will start with our function, Taylor series. What's f of Taylor series says? Cosine x, f of x here, which is cosine x, can be presented as what? As f of a, which is f of, what's a here? Pi over 2, plus f prime at pi over 2 times x minus pi over 2 to the power 1 over 1 factorial. So this is over 1 factorial, and the power here is 1, plus f double prime at pi over 2 times x minus pi over 2 square over 2 factorial, plus f triple prime at pi over 2 times x minus pi over 2 cube over 3 factorial, plus the fourth derivative now at pi over 2 times x minus pi over 2 to the power 4 over 4 factorial, and we proceed. As I mentioned before, the best presentation is to go up to the fourth derivative. Alrighty, so what's our target now? Is to present and find the values of those functions. So what do? We have to look f of pi over 2, this is a constant. F prime pi over 2 is a constant. F double prime is a constant. Triple prime is a constant. Those are constants that you need to find. Okay, how do we find it? We know that f of x is equal cosine x. So this implies that f of pi over 2, which is this one, is equal to cosine pi over 2. And we all know that cosine 90 is a 0. Now we go to the derivative. So now we're done with this one, guys. The f of pi over 2 is done. Now where do we go to? F prime of x, the derivative of cosine, is negative sine x. So this implies that f prime at pi over 2. So now we are in this term, f prime at pi over 2 is minus sine pi over 2. And we know that sine pi over 2, sine 90 is 1. So the answer is negative 1. F triple double prime of x. The derivative of sine is cosine. So this is minus cosine x. So f double prime at pi over 2 will lead to minus cosine pi over 2. Again, cosine 90 is a 0. So now let's go to the third derivative, guys. The derivative of cosine is minus sine, and there is a minus, so it becomes what? So it becomes sine x. And the third derivative at pi over 2 is sine pi over 2, and this is 1. Finally, let's go to the fourth derivative of x. The derivative of sine is cosine, as you see. Now the loop is done. I went back to where I started with, as you see, at the fourth derivative. So this implies that the fourth derivative at pi over 2 is cosine pi over 2 again, which is 0, and the derivatives continue. But this is the first four derivatives. So what do we do now? We go back to our functions. All right, so we can say cosine x, which is we started with here, is f of pi over 2, which is 0, plus f prime is -1. So what do we say? We're going to go back and replace this one with a -1. So this is, go back to the color, to the pen, sorry. So this is minus x minus pi over 2 of 1 over 1 factorial. Let's go to fw prime. Fw prime is here. So this one is plus 0 times x minus pi over 2 square over 2 factorial. This one comes here, the third derivative. So we have the third derivative is 1, so plus x minus pi over 2 to the power 3 over 3 factorial, because it's 1. The last derivative is 4, is 0, so plus 0 times x minus pi over 2 to the power 4 over 4 factorial, and we say plus plus. All right, so now let's see who survived the whole thing here. Definitely this is all 0, this is 0, this is 0. So what am I left with? So we can say that cosine x can be presented as what? As minus x minus pi over 2 to the power 1 over 1 factorial. Then the next one is this one. So plus x minus pi over 2 to the power 3 over 3 factorial. Plus what? See, now the trend somehow shows, huh? 1 factorial, 3 factorial, negative, positive. So the next one has to be a negative value. So we replace this positive with a negative value. So we say now the next, my expectation is, try it, you will find that the next term is a negative because now the trend shows, okay? So minus x minus pi over 2 to the power 5 over 5 factorial, and we proceed. So what's the presentation here, guys? Let's look at the presentation. What is this equal to? Look at the power, 1, 3, 5. So I can say this is x minus pi over 2 to the power 2n plus 1, since it's odd, over 2n plus 1 factorial. Now, of course, always n starts from 0 to infinity. Now let's look at the signs, guys. The first term is negative. So I'm going to say, okay, let's start with minus 1 to the n. If I put 0 here, -1 to the 0 as a first term, we get positive, but the first one has to be positive, negative. So what do? Either I subtract 1 or add 1, it doesn't matter. So I'm going to say this is n plus 1. So it's -1 to the n plus 1. And this is the final presentation of cosine x, guys, around x equal pi over 2. Right? So this is how you present your functions using Taylor series. All right. The next one. Let's look at ln function, the logarithmic function. Same thing, we say that f of x, which is equal to ln x, is equal to always f of a. So it's f of a. A here is given to be 1 plus f prime at 1 times x minus 1 over 1 factorial plus f w prime at 1 times x minus 1 square over 2 factorial. As I mentioned, you always go to the fourth derivative to see how the trend goes. 3 over 3 factorial plus f fourth derivative at 1 times x minus 1 to the power 4 over 4 factorial and goes on. So this is the Taylor series presentation or expansion of ln x at 1. Now, as usual, we have to look for those values. So we start with what? This one. So we have f of x is equal ln x. So this implies f of 1, I'm trying to find this now, it's ln 1. And we know that ln 1 is what? Is a 0. Now let's differentiate. F prime of x. Do you remember what's the derivative of ln x? It's 1 over x. So which implies that f prime at 1 is 1 over 1, which is 1. So now we got this, guys. Now fw prime of x. The derivative of 1 over x, you know, this is x to the minus 1. When you differentiate, it will be minus x to the minus 2. So this is minus 1 over x squared. And this implies that fw prime at 1 is going to be negative 1 over 1 squared, which is negative 1. Let's go to f triple prime at 1. So by the way, this is the derivative of minus 1 over x squared. I need to differentiate this, right? It's a derivative of the second derivative. So the third derivative is the derivative of this function. And this is the derivative of minus x to the minus 2 derivative, isn't it? You bring x squared up. And the derivative of that minus 2 goes down times minus. What do we get? We get 2x to the reduce the power by 1. And this is 2 over x cubed. So this is the third derivative of the function. So which implies that the third derivative of the function at 1 is 2 over 1 cubed, which is again 2. Finally, let's look at the fourth derivative of the function. The fourth derivative is the derivative of this one, or it's the derivative of that. So it's 2x to the minus 3 derivative, right? It's a derivative of this. So the fourth derivative is the derivative of the third derivative. And this is equal to, the power goes down, so it's going to be minus 6x to the minus 4, which is minus 6 over x to the 4. And this is implying that the fourth derivative at 1 is negative 6 over 1 to the 4, and 1 to the 4 is 1, so the answer is negative 6. So this is the fourth derivative of the function, guys. So what do we go now? Now we go back to our presentation. Simply, we go back to the red one. Our function is ln, so we can see, therefore, ln x is equal to f of 1. F of 1 is what? 0, so the first term is 0. Plus now f prime. F prime at 1, this one, the second term is 1, here it is. 1 times what? So plus x minus 1 to the power 1 over 1 factorial. Plus, let's look at fw prime. Fw prime now, guys, is minus 1. So now we need this one. Huh? Fw prime is not minus, so we say minus x minus 1 to the power 2 over 2 factorial. How about the third derivative? We are here now. The third derivative is 2, and it's positive. We say 2 times divided by 3 factorial times x minus 1 cube. The fourth derivative is negative 6, so minus 6. So we are here now. Minus 6 over 4 factorial times x minus 1 to the 4, okay, plus dot dot. So now let's simplify, by the way. This 0 goes away. So what do we get? 0. Now look at this one. The second term is x minus 1 to the power 1 over 1 factorial. 1 factorial is 1. The next one is minus So my apology, I shouldn't write the 0 here. So I need to get rid of this 0 actually. So let's remove the 0. So here it is again. So we start with x minus 1. This is our first term. X minus 1 to the power 1 over 1 factorial. The second one is minus what? X minus 2 square over 2 factorial is 2 times 1, which is 2. The next one is plus 2 over, by the way, 3 factorial is 3 factorial here is 6. 3 times 2 times 1 is 6 times x minus 1 cube. Then minus 6 over 4 factorial is 4 times 3 times 2 times 1. 4 times 3 is 12. 12 times 2 is 24. So this is 24 times x minus 1 to the power 4. And then we say what? Plus dot, dot, dot. We proceed. Which is, again, let's simplify it more. So the first term is just x minus 1 to the power 1, isn't it? Look at the second term is minus x minus 1 square over 2. The third term, look at this, 2 with 6 is a 3. So what do we have? X minus 1 cube over 3. The next term is 6 with 24 is 4, as you know. So this is x minus 1 to the power 4 over 4. So what do you expect the next one to be? Look at this one. X minus 1 to the power 1 over 1. 2 over 2, 3 over 3. So 4 over 4 because it alternates positive, negative, positive, negative. So I know the next term is going to be positive what? X minus 1 to the power 5 over 5 and goes minus and then proceed. Now let's present this function as a power series. So the final thing will be what? Be as follows. So it's the sum. Look at the power. 1, 1, 2, 2. So I can easily say it's x minus 1 to the power n over n, isn't it? 1, 1, 2, 2, 3, 3. So I can take it as n, where n starts from where now, as you see, I can't put 0, so n has to start from 1 to infinity. So this ln does not start with 0, because remember, n itself, the ln is not defined as 0, so this is how it goes. Now, look at the first term. The first term is positive. Because it's positive, I can just put minus 1 to the what? To the n. So it's minus 1 to the n. X minus 1 to the n over n is the presentation of ln x around a equal to 1. So I was able to present my function as what? As an infinite degree polynomial, which is called the Taylor series. Alrighty, so now he wants also in this one, find the radius and interval of convergence, something we have done before, okay? So now we find the presentation. Here's the presentation, guys. So I'm gonna copy it down. So we have the sum, minus 1 to the n, then x minus 1 to the n over n, where n is equal 1 to infinity. This is our f of x. This is who? This is ln x. Can be presented this way. Now, to find the radius of convergence and interval of convergence, guys, what do? We take the limit of an plus 1 over an as n goes to what? To infinity. What is this equal to? This is equal to the limit as n goes to infinity of the following. An plus 1, guys. This is our an. So an here is minus 1 to the n, then x minus 1 to the n over n. This is the an. Okay, so this is equal to, let's look at an plus 1. So what will be an plus 1? I'm going to replace every n with n plus 1. So it's minus 1 to the n plus 1 times x minus 1 to the n plus 1 divided by n plus 1. Now, this is divided by, I'm going to change it to multiplied by. Divided by an, multiplied by an. So if you change division to multiplication, what do you do for an? You take the reciprocal of that. So I'm going to flip this, guy. So n goes up, minus 1 to the n goes down, and x minus 1 to the n goes down. See, this is an flipped. Now, what do we say? Now, this is equal to the limit as n goes to infinity. Let's look at this one. I'm going to expand this one, guys, as minus 1 to the n times minus 1, isn't it? To the power 1. I can expand this one to this. Same thing here. This is x minus 1 to the power n times x minus 1 divided by n plus 1. In the second part, there isn't much to do. So this is n over minus 1 to the n times x minus 1 to the n. Now, what happens here is the following. This x minus 1 to the n goes with x minus 1 to the n. Minus 1 to the n goes with minus 1 to the n. So what am I left with? So let's see what is left after all of this. So this is equal to the limit as n goes to infinity. I'm going to split the x's from the n's, okay, and the constant. So we have minus 1 to the n here over n plus 1, and there is n. So what I'm left with is the following. Minus n, you see, on the top, minus 1 times n is minus n over what? Over n plus 1 times the absolute value. Now let's look at the x's. What am I left with? Absolute value of x minus 1. So far, so good. This is for the x's. Now, don't forget that n starts from 0 to infinity in the polynomial, right? So it starts from 1 to infinity. So n is always positive. So this is equal to the limit as n goes to infinity. The absolute value of negative 1 is what? It's positive 1, right? So this is like the absolute value of my negative 1 times the absolute value of n over n plus 1 times the absolute value of x minus 1. I can distribute the absolute value over the constant, the n's, and the x's. But the absolute value of negative 1 is 1. And this is equal to the limit as n goes to infinity. Now, so this is nothing but 1. How about this? Look, n starts from 1. I know everything inside is positive. So can I remove the absolute value? Yes, we can. So this is n over n plus 1 times x minus 1. All right. Now, let's look at this part here, guys. If you put infinity, I'm going to write it here, the limit of n over n plus 1 as n goes to infinity. There are so many ways to do it. One way is, I know that this is infinity over infinity. So what do we use? By L'Hopital rule. So this is going to be the limit as n goes to infinity. The derivative of the top as x or as an n is 1. Same thing at the bottom is n. 1 over 1 is 1. So the final answer is 1. So this is equal. So this is all is 1. So the final answer is what? Is x minus 1. Since the coefficient of x is 1, there was nothing there. So this is like x minus a. Remember the radius of convergence? Usually, it is convergent whenever this is what? Is less than 1. So now, who is this on the right-hand side? Now, this one is our r. So our radius of convergence is 1. This is the radius of convergence. So this one is convergent with a radius of 1 around what? Around A. So here is A, guys, equal 1. So it's convergent a little bit before and after that. Right? Here is, it is convergent at A. We know that the power series is convergent at A. And it's 1 radius. So if I go 1 to the left, it's a 0. And 1 to the right is what? Is 2. This is the meaning of it. Okay, what would be the interval of convergence, guys? To find the interval of convergence now, so now we're done with the radius of convergence. Now let's talk about the interval of convergence. So I'm going to go to the blue. To find it, guys, we go back to our final result of the radius of convergence. What do we have, guys? We have x minus 1 is less than 1. In mathematics, what does that mean? That means x minus 1 is less than 1 and greater than what? Negative 1. Add 1 to both sides, add 1 here, and add 1 here. What do we get? This cancels that. So x is between 0 and 2, as I mentioned a minute ago. So what do we do now? So I know that the radius of convergence is between 0 and 2. But do you think we should include the 0 and the 2? We don't know. So let's check now. So here, I'm going to let x equal 0. I'm going to start with x equals 0. Where do we plug it, guys? We plug it back into our function, which is here. So what do we get in this case? We have the series n equal 1 to infinity, negative 1 to the n times 0 minus 1 to the n over n. And this is equal to the sum of minus 1 to the n times minus 1 to the n over what? Over n, where n is equal 1 to infinity. Minus 1 to the n times minus 1 to the n is minus 1 to the 2n, right? We add them over n, where n equal 1 to infinity. But we know that this is an even power. So this is what? This is 1 over n, where n equal 1 to infinity. Now, what is this? This is what we call harmonic, isn't it? This is harmonic series, which is divergent. So what do we conclude? Therefore, the series is divergent at x equals 0. Now, what do? We take the other case. So let me remove that series thing here, that limit thing, and try to find now what happens with 2. So I'm going to go here. When x now is equal to 2, I'm going to take the other case when x is equal to 2 and plug it in the series. What do we have, guys? We have n equal 1 to infinity. I'm going to go back here again. It's minus 1 to the n times 2 minus 1 to the n over n. And this is equal to the sum n equal 1 to infinity. Now this is minus 1 to the n. 2 minus 1 is 1 to the n, right? Over n. But 1 to the n is 1, as you know. This is nothing but 1. So what am I left with? I'm left with negative 1 to the n over n, where n is equal 1 to infinity. Remember, what kind of series is this? This is what we call alternating series. Okay. By the way, we did the same example. Go back to the alternating series section, and you will find that we showed that this is convergent. How? Do you remember the alternating series? We look at Bn. What's Bn here? Take the series without minus 1 to the n. What am I left with? 1 over n. What's the first condition supposed to be? The limit of Bn has to be 0, right? Let's check it as n goes to infinity. What's the limit as n goes to infinity of 1 over n? We know this is 1 over infinity, which is what? 0. The second condition is that this Bn has to be decreasing. How? I'm going to let f of x change Bn to a function, which is 1 over x, and differentiate it. What's the derivative of that? It's minus 1 over x squared. And this is positive multiplied by minus. We all know that this is always less than 0. So it is what? When the derivative is always less than 0, so the function is decreasing. So the second condition is satisfied. The first condition is satisfied. So what do we conclude? So we conclude that the series is convergent at x equal to. So far, so good. This is what we have in this. So here, I'm going to put my final result. So what is the interval of convergence? So I'm going to box it here and say the following. Therefore, the interval of convergence is what? Remember, it's not convergent at 0, so we open it at 0, but it was convergent at 2, so we close it at 2. And this is the interval of convergence of this function. Alrighty? So if we go back to some of those functions we just did a minute ago, we took the cosine. Yeah, we finished the cosine, right? Look at this. The presentation of the cosine is this one. He says, find the radius of convergence. Can you find the radius of convergence of this one? Of course we can. So what do? I will take this one, guys, and present it. So let's look. Here it is. I copy it down. All right. So to find the radius of convergence, what do we take? We take the limit of an plus 1 over an as n goes to infinity. And this is the limit as n goes to infinity of the following. Let's start with an plus 1. By the way, this is your an. If I make an plus 1, what do we end up with? Minus 1 to the n plus 1. So I'm going to replace this one with n plus 1. Plus 1 is going to be what? Here it is, plus 1, which is actually n plus 2. Then what? Times x minus pi over 2 to the 2, then n plus 1 plus 1. You see, I'm replacing every n with n plus 1, divided by 2n plus 1 plus 1, all factorial. This is, guys, an plus 1. I am replacing every n with n plus 1. Divided by, I'm going to change it to multiplied by what? The reciprocal of that. So the denominator here, which is 2n plus 1 factorial, goes up, and minus 1 to the n plus 1 goes down, and x minus pi over 2 to the 2n plus 1 goes down. This is what we do for the reciprocal of an. And this is equal to the limit as n goes to infinity of the following. Now I'm going to expand this one. This is, as you know, minus 1 to the n plus 2. So I will make it n plus 1 times minus 1 to the 1, isn't it? I can do it this way. Right? I split it to two pieces, n plus 1 and then 1. The second part is x minus pi over 2. How can I write this one? Open this. This is 2n plus 2 plus 1, which is 2n plus 3. Right? This is the power here. Over. This one is 2n plus 2 plus 1 again is 2n plus 3 factorial times 2n plus 1 factorial over minus 1 to the n plus 1 times x minus pi over 2 to the power 2n plus 1. All right, so let's split this one, guys. So this is the limit as n goes to infinity. How do we do this? Now, minus 1 to the n plus 1, as you see, goes with that. So what's left here is minus. Look at this one. This can be written as x minus pi over 2. Look, I'm trying to match this power with this power, 2n plus 1 and 2n plus 3. So how can I write this one? Isn't this 2n plus 1 times x minus pi over 2 square? Can we do that? Because a square plus 1, 2 plus 1 is a 3. Here it is. So I split this one, 2n plus 1 to 2n plus 1. Why 1? Because in the denominator I have 2n plus 1, and then what's left is 2, which is a square. Divided by, now let's look at this one. The first term here, by the way, is 2n plus 3, isn't it? That's the first term. How do you take the factor? What's the factorial of a number? It's the first number is n, then what? Then reduce it by 1, then reduce it by 2, and you keep on till you reach to 1. So this one can be written 2n plus 3 factorial. The first term is 2n plus 3. Who's next? 2n plus 2. Who's next? 2n plus 1. Do I have to continue? No, I'm going to stop here and put what? Put a factorial. Why did I stop here? Because here I have 2n plus 1 on the other side. I have 2n plus 1 in the numerator here, so I stopped here at 2n plus 1. Divided by x minus pi over 2 to the 2n plus 1. So look what happens. This goes with that. This one all goes with that one. So what am I left with? I'm left with the limit as n goes to infinity of what? On the top, I'm going to take the minus. Let's take the n's only, guys. So what is this? 1 over, there is no n on the top at all, left 2n plus 1, sorry, 2n plus 3, and 2n plus 2, times the absolute value of x minus pi over 2 all squared, isn't it? This is all squared. Now remember again, the absolute value of negative goes away. So this is equal to the limit as n goes to infinity of 1 over 2n plus 3 and 2n plus 2. Here I can remove the absolute value. Why is that? Because I have x minus pi over 2 all squared. So this is x minus pi over 2 all squared. But what's the limit of this one, guys? If I put infinity, what do we get? We get 0, by the way, and you can keep the absolute value. If I put here infinity, we get 0, right? Anything over infinity is 0, so the answer is 0. So no matter what, the limit is 0 times anything is 0. So this is always less than 1, isn't it? So what does that mean? That means the radius of convergence is what? Is infinity. So this function, cosine, is convergent everywhere. Okay, this is what I can conclude from that. Again, why is it infinity? You see, you are supposed to get, so this is 0 times this, x minus pi over 2 square absolute value. Okay, so if you want to detail that one in more details, you can do it this way. So this is 0 times x minus pi over 2 square. What do I need this? I need this to be less than 1, isn't it? To be convergent, I need this to be less than 1. Okay, but what is this? This is always what? 0. Is 0 always less than 1? Yes, 0 is always less than 1 for what? For all x, isn't it? No matter what you take x, it's always going to be 0. So that means because this is true for all x, so the radius of convergence is infinity. For x, what's the center, by the way? The center here is pi over 2. So what is the radius of convergence? Everywhere. So this function, this series is convergent everywhere. Okay, so the cosine is convergent everywhere. Okay, and then we did this one. So we proceed now with e to the x. What's the McLaurin series for this one now? Okay, so we need to find the McLaurin series. So now we are moving to the McLaurin, guys. All right, what does McLaurin say? It says f of x is equal to f of 0, the expansion, plus f prime at 0 times x over 1 factorial, plus f double prime at 0 over 2 factorial times x squared, and goes on, by the way. Here, I don't have to go further because I know that my function e to the x is always the same derivative, right? Okay. So this is our function, which is e to the x. So this is our e to the x function. All right, so what's our job now is to find those values, right? So let's see, f of x is e to the x. So this implies that f of 0 is e to the 0 and e to the 0 is 1. How about f prime of x, which is the second one here? F prime of x is e to the x again. So f prime at 0 is again e to the 0. Which one again? So no matter how many times you differentiate it, okay, fn of x is e to the x, which implies that any derivative you take At 0, you will end up with 1, isn't it? So what do we say? Therefore, e to the x, our function e to the x, is f of 0, which is 1, plus f of prime 0 is 1 again. So it's x over 1 factorial, plus again, this is 1. So 1 over 2 factorial times x squared, plus 1 over 3 factorial times x cubed, right? And goes on, isn't it? So how do we present this as a series, guys? What do I notice here? The power is 1, the power is 2, the power 3. So it's x to the n over what? When this is 1, 1 factorial. When this is 2, this is 2 factorial. When this is 3, 3 factorial. So over n factorial. And don't forget, n starts from what? From 0 to infinity. So what happens to the 1? It's there. Look at this. When n is equal to 0, and you put it here, x to the 0 is 1 over 0, 0 factorial, which is 1, and this is the first term. So when n is equal to 0, will give me the first term. Is this alternating series? No. So that's it. You're done. This is your series. So e to the x can be presented this way. Now, what do we need to find? The radius and interval of convergence. So now let's go to the radius of convergence. What do? We take the limit of an plus 1 over an as n goes to infinity, which is here equal to the limit as n goes to infinity of what? An plus 1. This is, by the way, is our an. That's our an. Replace it with n plus 1. So you have x to the n plus 1 over n plus 1 factorial divided by an. I'm going to say times reciprocal of that, which is n factorial over x to the n. Now we expand the first term. So this is n goes to infinity of what? X to the n plus 1 can be split into x to the n times x to the 1, isn't it? Divided by n plus 1 factorial. Let's look at this term, guys. What's the first term? I know it's n plus 1. Now reduce it by 1. What am I left with? With n. Do I have to say then n minus 1? No. I'm going to stop here and say what? N factorial, because on the top I have n factorial. Times the top is n factorial divided by x to the n. Now this n factorial cancels this n factorial, x to the n cancels this x to the n. What am I left with? We are left with the limit as n goes to infinity of what? Let's look at the n's, guys. There is no n on the top at all, so it's 1 over. At the bottom, I have only n plus 1. Here is n plus 1 times what? Let's look at the x's. What do I have? I'm left with x only. That's it. And we put absolute. Now what happens is that the limit as n goes to infinity goes to the 1 over n plus 1. By the way, I removed the absolute value from n plus 1 because I know n starts from 0 to infinity. So it's always positive. Times what? I'm going to give the absolute value for x, and we don't have to take the limit here because the limit is talking about n. And we know that this is equal to what? 0. Anything over infinity is 0. So the answer is 0 times absolute value of x. And 0 times absolute value of x is equal to 0, which is always less than 1, right? 0 is always less than 1. For what? For all x. So what's the radius of convergence here? It's infinity. So this series, guys, so this series here is convergent where? It's convergent at the center. What center are we talking about? McLaurin is what? 0. It's convergent at 0, and it's convergent everywhere after 0 and before 0. So it's convergent everywhere. Centered at 0, and it's convergent to the right and to the left of 0. Okay. Let's proceed with sine x. What's the McLaurin series of sine x, guys? Again, we write down sine x is equal to our function f of x according to the Taylor series. It's equal to f of 0 plus f prime at 0 over 1 factorial plus f double prime at 0 times, we forgot actually the x here, times x squared over 2 factorial plus f triple prime at 0 over 3 factorial times x cubed plus f fourth prime at 0 times x to the 4 over 4 factorial and goes all the way to infinity. So it's the same thing as McLaurin, by the way. This is a McLaurin, but a here is a 0. All right. So what's our target now is to find the values of the following functions. We need to find f of 0, f prime of 0, f double prime of 0, triple prime, and the fourth derivative. So let's start with this one. So f of x now is sine x. So now let's replace x with 0. So what's f of 0? It's sine 0. We know that sine 0 is what? Is a 0. Now we go to, so now this one represents the first function, which is this one, first value here. Now f prime of x, the derivative of sine is cosine x. Now let's put f prime at 0. What happens? It's cosine 0, and cosine 0 is 1. Who's this? This is the second function, which goes all the way here. This is the second one. F double prime at x, the derivative of cosine is minus sine x. And this implies that f double prime at 0 is minus sine 0. And we know that sine 0 is 0. F triple prime of x is minus, the derivative of sine is cosine x. So f triple prime at 0 is equal to minus cosine 0, which is negative 1. Finally, the fourth derivative of x is sine x, as you know. So this implies that the fourth derivative at 0 is sine 0, which is 0. 4 is good enough. Now let's go back to our function. Therefore, so we go to the color of the function we started with, sine x. What is it equal to? It's f of 0, which is 0. So the first term is 0, guys. The second term is 1. F prime of 0 is 1, so it's plus 1 over 1 factorial times x. Let's go to f double prime, which is here. F double prime is a 0, so this one goes in here. So we have 0 times x squared over 2 factorial. How about the third derivative? The third derivative is negative 1, so this must be replaced by negative 1, so minus 1 over 3 factorial times x cubed. The next one is 0. The fourth derivative, here is the fourth derivative, it's a 0. This one is a 0 over 4 factorial times x to the 4, and goes on. 0 goes away, this 0 goes away, this 0 goes away. What am I left with? It's x to the 1 over 1 factorial. The next one is minus 1 over 3 factorial, and on the top I have x what? x3. So what do you expect? Positive, negative, then positive. 1, 3, so I'm expecting what? 5, isn't it? Over 5 factorial. Who's next? Minus x to the 7 over 7 factorial, and goes on, guys. So how can I present this one as a power series? So this is equal to the sum. Look what we have, guys. X to the 1, x3. The powers are odd. So this is x to the what? 2n plus 1 over 1 factorial, 3 factorial, 5 factorial. So it's the same thing. So 2n plus 1 factorial. And what do we say? N equals 0 to infinity. Now, the first term is positive, so I can say times minus 1 to the n. So this is, guys, the McLaurin series presentation of the sine x. Now, what do we need to find? The radius of convergence. To find the radius of convergence, what do we do now? We take the limit. So let's go to the radius of convergence. So we're going to take the limit of an plus 1 over an as n goes to infinity. This is equal to the limit as n goes to infinity of an plus 1, guys. I'm going to go to this one. By the way, this is your an So what do we say? Minus 1 to the n plus 1. Then x to the 2 times n plus 1 divided by 2n plus 1 factorial. Be careful here. I'm replacing every n with n plus 1. You see, every n is replaced with n plus 1. Divided by, I'm going to say times the reciprocal of this. So 2n plus 1 goes on the top. And minus 1 to the n goes down. And x to the 2n plus 1 also goes down. So I took the reciprocal of an. Now this is equal to the limit as n goes to infinity. I'm going to expand this to minus 1 to the n times minus 1 to the 1, isn't it? And this one, by the way, is 2n plus 2 plus 1 is 2n plus 3, isn't it? So this is x to the 2n plus 3 divided by, same thing, 2n plus 3 factorial. And here is 2n plus 1 factorial divided by minus 1 to the n and x to the 2n plus 1. Now, I need this x to the 2n plus 3 to match this. So I'm going to write it this way. So this is equal, guys, to the limit as n goes to infinity of what? This is minus 1 to the n. By the way, let me remove this one actually. Minus 1 to the n, as you see, goes with this one. Huh? So I have only minus 1 times x to what power? I'm going to make 2n plus 3 to be 2n plus 1 times x squared. How about that? Because when you multiply, you add them, right? 1 plus 2 is 3. So I can write it this way. All right, divided by. Same thing in the denominator. We did it a minute ago. So I'm going to write this one. Who's the first term? 2n plus 3. Who's next? 2n plus 2. Who's next? 2n plus 1. And goes on. So I'm going to stop here and put factorial. Why? Because on the top here, I have 2n plus 1. So times 2n plus 1 factorial over x to the 2n plus 1. Very nice. This one cancels that one. 2n plus 1 factorial goes with that. So I'm left with the limit as n goes to infinity. We don't care about the minus anyway, by the way, remember that? So I have 1 over 2n plus 3 times 2n plus 2. And this is times the absolute value of x squared. But we know that this limit is 0. So we get 0 times x squared, which is 0, which is always less than 1 for what? For all x. So this series is always less than. So this limit is always less than 1 for all x. So the radius of convergence is what? So we can conclude here on the top. So let's conclude the whole thing. So now we can conclude the following. Therefore, the series, the interval, so the radius of convergence is r equal to infinity. And in this case, the interval of convergence is what? Will be from negative infinity to infinity. Now, don't forget, McLaurin series, it's the 0. So this series, sine x, this series that we found, which is this one, is definitely convergent at 0. Where else? It's convergent everywhere at 0, which is the center of convergence, and everywhere to the right and to the left. All right. So what do we have, guys, now? Let's do the last one. How about the McLaurin series of cosine x? Same thing. We say cosine x, which is our function f of x, is equal to f of 0 plus f prime at 0 over 1 factorial times x plus f double prime at 0 over 2 factorial times x squared plus f triple prime at 0 over 3 factorial x cubed plus the fourth derivative at 0 times x to the 4 over 4 factorial, and we proceed all the way to infinity. Alrighty, so now let's go and find those values. Which values we're going to look for? We're going to look at f of 0, f prime of 0, f double prime of 0, triple prime, and goes on. So what do we have here, guys? We have f of x. Go back to your function, it's cosine x. So this implies that f of 0 is cos 0, and we know that cosine 0 is 1. Now let's look at, so what did we just find? Who's this one? This one is exactly f of 0. Now let's find f prime of 0. So I'm going to first find f prime of x. The derivative of cosine is negative cosine x. So what does this imply? F prime at 0 is negative cosine 0, which is negative 1. So now we got f prime at 0, guys. Now let's go to f double prime of x, which is actually the derivative of cosine is minus, and there is minus, so it's going to be sine x, which implies that f double prime at 0 is going to be sine the 0, which is 0. F double prime, triple prime of x, sorry, the derivative of sine is, oh, I did a mistake here, sorry, my apologies. So let me just fix that thing, eraser here. Okay, just minor thing, because the loop is not coming. I noticed that the loop is coming fast, so I can immediately figure out my mistake. The derivative of cosine is minus sine x. And f prime of this is minus sine 0, which is 0. The derivative of sine is cosine, so this is minus cosine x. So this is minus cosine 0, which is negative 1. The third derivative, the derivative of cosine is minus, so it becomes sine x. And this implies that the third derivative at 0 is definitely going to be sine 0, which is 0. And finally, let's go to the fourth derivative of x. The derivative of sine is cosine x, and the fourth derivative at 0 is cosine 0, which is 1. So we came back to the loop. So the loop started with cosine, ended up with cosine. So now what do we say? Now we go back to our function, our question. So what do we have? Therefore, cosine x can be presented as what? F of 0 is 1. So the first term is 1. Plus f prime of 0 is 0. So this one is a 0. So it's a 0 over 1 factorial times x. F double prime is negative 1. So minus x squared over 2 factorial. The next one is 0. So plus 0 x cubed over 3 factorial. The next one is 1. So plus 1 x to the 4 over 4 factorial, and goes on. Okay, guys, so things continue. So look what we have now. So this is equal to, the first term is 1. This is dying, 0. This is 0. So what's after 1? Minus x squared over 2 factorial. The next one is plus x to the 4 over 4 factorial. So look at the trend. 2, 4. So what do I need? I need x to the 6 over 6 factorial. Positive becomes negative. So plus, minus, and goes on. Plus, and we continue. Now let's present this one as a series. You look at the power, it's even. So what do we say? X to the 2n over, because 2 factorial, 4 factorial. So because also the denominator is the same thing. So this is 2n factorial. Now it alternates. So I'm going to say minus 1. This is start with n, guys. If I started with n equals 0, what's minus 1 to the 0? It's 1, which is positive, and this will do it actually. True. Because also if you put a 0 here, x to the 0 is 1. 0 factorial is 1. So if I take n equal to 0, this will give me 1, which is the first term. So now I'm done. And this is the McLaurin series presentation of our function. So we're done with the presentation. What would be the radius of convergence? So to find the radius of convergence, guys, we will do the following. All right. Take a color to be green. We're going to take the limit of an plus 1 over an as n goes to infinity. This is the limit as n goes to infinity. Now this is, as you know, this is your an. So it's minus 1 to the n plus 1 times x to the 2 times n plus 1. Don't forget, you replace n with n plus 1 divided by 2 times n plus 1 all factorial times the reciprocal of an in the denominator is the reciprocal of this, which means I'm going to put 2n factorial on the top minus 1 to the n at the bottom, and x to the 2n goes at the bottom. And this is equal to the limit as n goes to infinity. Now, if you look carefully at this one, this can be split into minus 1 to the n times minus 1, right? This is 2n plus 2. So I'm going to make it x to the 2n times x squared, right? This one is 2n plus 2. This one, you open the bracket, you get 2n plus 2. I'm going to split it to 2n and 2 over. Now, what is this, by the way? This one here is 2n plus 2 factorial, isn't it? So the first term is 2n plus 2. Here it is. What's the next term? Definitely, it's 2n plus 1, right? And what I'm going to do, what's the next term? It's 2n. It keeps on reducing, right? Then I'm going to stop here and say factorial. Now, on the other side, you have 2n factorial divided by minus 1 to the n times x to the 2n. So now x to the 2n goes with x to the 2n. 2n factorial goes with this 2n factorial. Minus 1 to the n goes with minus 1 to the n. What are we left with? So this is the limit as n goes to infinity of, look at the n's first, guys, and the constants. I have only minus 1 on the top. So I have negative 1 over 2n plus 2 and 2n plus 1. This is for the n's. How about the x's? The only thing left is x squared. And it's very obvious here that the limit as n goes to infinity, 1 over infinity is a 0, so this is 0. So the answer is 0 times x squared, which is equal to 0 for any x. So, and this is always less than 1 for all what? X. So now the conclusion. What do we conclude from all of this? We conclude the following. Therefore, the radius of convergence is r equal to what? Infinity. As you notice here, this is less than 1 for all. By the way, what is the center here? The center of convergence is 0, according to McLaurin. It's convergent at 0. Where else? Everywhere else, to the right and to the left, because r is the radius. Since r is going to positive, negative, infinity, therefore, interval of convergence is what? Is negative infinity to infinity. And this is the interval of the cosine. So cosine, the presentation for cosine as a power series, which is McLaurin series, here it is. And the radius of convergence is minus infinity to infinity. And this, guys, will conclude the table. Everything here, you know, we did this one in the previous one, remember? We did it in the previous sections. Ex, we did it today, and the radius of convergence is infinity. Sine x, the McLaurin, we did it, and the radius of convergence is infinity. Same thing for cosine, the radius of convergence is infinity. Tangent inverse and ln, we did them in the previous sections, right? And the radius of convergence is 1 and 1. This is a table, guys, you have to always to keep with you in order to proceed to the next sections, because those are useful now. In why are we studying all of this? Why? Because functions, sometimes you can't do certain things for these functions like sine, cosine, tangent, inverse, natural logarithm. So what do? We represent it as a power series, which is this infinite series, and then we can apply whatever I want to the function by applying it to the Taylor series or the McLaurin series of the function. So this table is very crucial. It's very important for you to memorize it sometimes or to keep it with you, right? And this will take us to the second trip in our work, which is going to be more in Taylor series and how do we use Taylor series of some other functions. We'll see you in the next section. You guys have a good day.